You can tell what element something is made out of by which wavelengths it cares about, by which wavelengths it absorbs. So, here we go. What does all of this have to do with the spectrum? How does this actually look? Here we go. Here we go. Sorry, this is, like I said, this is probably one of the most complicated things that we'll cover. Now, here we go. If that is a mystery gas made of a mystery element, I don't know which wavelengths it's gonna like. So what I can do, this is okay. What I can do is, instead of trying to figure out what wavelengths it likes one by one by one by one, what I can just do is shine all of the wavelengths on it at the same time. So if I can make a perfect light that produces all wavelengths, I can shine all the wavelengths onto this atom. And what's going to happen to most of those wavelengths is that they're just going to pass through because the atom doesn't care about it. But a few of them will get captured by the element, okay? So, check this out. Here we go. Got another drawing I got to do, and of course it freezes up on me. Stop freezing. Here we go. So imagine, here we go. I've got a mystery gas right here. Let's call that gas. And let's say I've got a perfect light over here. That's like a light bulb, okay? Here's a perfect light. Now that perfect light is making all of the wavelengths for me. It's making all of them. And let's say I shine that perfect light through the gas. Now, like I said, most of that light will come right through the gas because this mystery gas only cares about certain wavelengths. But, here we go, what will happen to a few of those wavelengths? Well, the few of them will get trapped in the gas, okay? Most of the light of the perfect light will make it through, but a few of the wavelengths will get trapped. So, here we go. Like I said, we're almost done with this part. Here we go. So, if we had a perfect light, it will produce a perfect continuous spectrum because it's giving off all of the wavelengths. Nothing is missing. But if I were to put a mystery gas right here, and it steals some of the wavelengths from this light, what gets through is most of the rainbow. But what would happen to a few of the colors in the rainbow? Take a guess. Take a guess for me. See if anybody can figure this out. What would happen to a few of the colors in the rainbow if we put our mystery gas right here? Yeah, that's a good way to put it. Because the mystery gas is intercepting some of the wavelengths would be missing. Some would be gone. There would be holes in our rainbow that you wouldn't necessarily be able to see when everything's mixed together, but when you split it, you can see some holes. So it will go from this to this. Okay? See right here? Because this mystery gas is here, a few of the wavelengths are missing in our rainbow. A few of the wavelengths are missing in our spectrum. And if you turn that into a graph, see how we still have that hill shape on the graph? But a few, look what's happened to the graph wherever there was a missing color. Wherever there was a missing color, the intensity has dipped down to very dim. It looks sort of like icicles, okay? These are missing colors in the graph, okay? And because this shape of spectrum was caused by this gas absorbing some of the wavelengths, we call this, instead of a continuous spectrum, it's called an absorption line spectrum. Good question, but we don't have a perfect light to test that. That is a good question. So this experiment can never be perfect, but we can produce lights that are very close to perfect. And as long as we know which anomalies are present in our source, then any new anomalies that show up because of the gas cloud, we know that they came from the gas cloud. But that's a good thing to point. So we'll never be able to do this absolutely perfectly, so we have to try to make a source that is very close to being a perfect light source. Okay? Now, here we go. Let's put it all together. Here we go. If we don't know what this gas is made out of, then we don't know what pattern's going to come out. But we know what pattern every element makes because we've tested them in the lab, right? So if we've got a mystery gas here, if we look over here and look at which colors are missing, what can we figure out about that cloud of gas based on which colors are missing here? What could we figure out about that cloud of gas? While you guys are trying to answer that, someone's saying, so we only know the elements we have. Yes. Although technically, every element has a certain pattern, and so does every molecule, like water and carbon dioxide and stuff like that. So we have every element that we have found on Earth and every molecule we've found on Earth, we know the pattern. But we can figure out what a mystery cloud of gas is made out of by... Yeah, we can figure out what elements were here based on which colors are missing here. So somebody's asking a question about mystery elements. There are times when we look at stuff in space and we find a pattern that doesn't match any known element or molecule that we have tested here on Earth. And in that case, what we have to do is we have to figure out, oh, that's made of something new that we've not experienced before. How many of those unknown things have we found? I don't personally know, but it's easily a lot of them. It doesn't usually mean, we don't expect, when we find a pattern that doesn't match a known element, we don't usually think we're finding a new element, but we do think that we probably usually think it's a new type of molecule, which is like a combination of elements stuck together, right? But yeah, that does happen. We have discovered new elements in space before. Let me show you one example real quick. This right here is the spectrum of hydrogen gas. So we see this spectrum all over the place. We know that we're looking at hydrogen if an object spectrum has these colors missing, these wavelengths. Remember, wavelengths are colors, right? So anytime we see this pattern, we know we're looking at hydrogen, okay?